Okay, welcome back everyone. Today we have Andy Berget telling us about Schubert variety of a pair of linear subspaces.
Thank the organizers for just tell you all about my results. The talk is going to have three parts. In the first part, I'm going to talk about Kempf collapsing, vector bundles, and in the second part, I'll talk about Grosvenor degenerations of these Kempf collapsings. And in the third part, I'll talk about how to extend some positivity results, or maybe some formulas that occur by passing from 1 to 2 to all matroids, extensions to all matroids. Okay. Part 1. I'm going to take E to be a vector bundle over X, which is going to be a complex projective variety. I want it to be smooth. So I'm going to make an assumption, which is that E is contained inside of a, so it's a subbundle of a trivial bundle, CM X. And I'm just going to denote this by CM with an underline to refer to CM viewed as a vector bundle over X. This product, or this vector bundle here, the trivial bundle, it comes with two projections. It has a projection to X, and it also has a projection to CM. I'll let I denote the projection to C to the M. And then the collapsing of E is the image of E under this projection mapping. So this is going to be some closed subvariety of C to the M. So it's an affine variety. So this is most interesting when so what I want is have a map of E to the projective variety. Which I'm going to denote the projective variety as Y sub E. And this is most interesting. Yeah. Oh, yes. Most interesting when this is birational. So I want to birational isomorphism. And so in general, if you take your favorite subbundle of a trivial bundle and you collapse it and the result was not a birational isomorphism, then there's like a general idea which you should try to like make this vector bundle a little bit bigger. One way to do that would be to just take direct sums of this bundle with itself. Okay. You take copies or a direct sum of this thing with itself, and then you collapse that bundle. It has a greater chance of being birational isomorphism here. Okay, so here's an example. So X is going to be the Grassmannian R-dimensional subspaces of an n of Cn. And S is going to be the homological subbundle of which is a subbundle of trivial bundle of rank n. Right. So if I, and then I'll fix some notation for later. Q is going to be the associated quotient bundle, which is C n modulo S. This is a good example. If I just collapse S, subbundle of a trivial bundle, sort of nothing happens. You should expect that just S by itself just collapses to all of C to the n. So what I'm going to do is I'm going to take a direct sum of S with itself a bunch of times. Okay, so A times. And so this will now be a subbundle of C and direct sum with itself, K times. And I can, so I'm going to think of, so when I project this thing, so when I look at Y sub E, this is now going to be some affine subvariety of Cn cross Cn. And I want to think of this as the space of K by N matrices. Okay. So each of these is a row of that matrix. So what is the collapsed variety? So here, in fact,
I didn't pass it your notation correctly.
sorry,
What direct sum of the right with product, or I mean, very mean.
So I'm going to take the direct
cross X cross C to the n, or do you mean the direct sum of C to the n's cross X?
Sorry, this is okay, this is the direct sum of vector bundles. So this is going to be Cn plus Cn plus Cn plus Cn cross X. Okay, so in this case, Y sub B is equal to the set of all K by N matrices rank at most R. So this is like a very famous variety to be studied. It's defined by the R by R minors of a K by N matrix of indeterminates. Okay, so example 2. I don't write it.
Does this turn out to be birational isomorphism?
It should turn out to be a birational isomorphism, provided that this condition of being rank at most R is vacuous when K is small. So what do I want? I want R to be I want the K to be bigger than R. And let's okay, so example 2. I'm gonna take X to be the wonderful variety of a linear subspace. So L here is some subspace of Cn. WL is its wonderful variety. What am I going to use for my my vector bundle? I'm going to take E to be O of negative beta. This is going to be a line bundle on WL, and it occurs by pulling back. Yeah.
Is it easy to remind people what the wonderful variety is?
So what should I say? It's a compactification of L inside of a product of projective spaces.
In the projectivization of that.
The projectivization of L. So in general, this is going to be some subvariety of the hedral variety. What would you?
That's it.
Okay. Okay, so in general, this thing is going to be some like closure of L inside of a product of projective spaces. And this line bundle is going to occur by pulling back one of the line bundles on one of the projective spaces. Okay, so what is Y sub E in this case? So it's easy to say what the collapse variety looks like over like a dense subset of WL. And so what it is I'm going to take the closure. Oh, I meant to say is that this is a subbundle of CBN, the trivial bundle arrangement. So that whatever the collapsed thing is going to be, it's going to be some affine variety in CN.
Andy?
Yeah.
Could you repeat what is beta?
What is beta? This WL, it's a subvariety of a product of projective spaces. And so WL contained in some product of projective spaces. Not all of the projective spaces are going to be PNs, but two of them will be. And there's going to be an O of -1 on here. There's going to be an O of -1 on here. One of these is going to pull back to a line bundle that would be O of negative alpha. The other one's going to pull back to a line bundle that's O of negative beta. So these are the like the alpha and beta that show up in the deep Presidio Hotcats paper. Okay, so what is this thing? So I'm going to take.
Fourth day.
Sorry, what?
So why E equals a bit, I can't.
Oh, so this is closure,
Closure, okay.
like Zariski closure.
Okay.
And now I have to fill in the blank here. So it's going to be the closure of all points. So the inverse of all points of L intersect the N torus T here is going to be C cross. Okay, so I'm going to look at all the points inside of my linear subspace that that I could possibly take the inverse of all of their coordinates, and I'll take the inverse of all of those, and then I'm going to close those things up. So this this variety, it has a name. So this is the inverse, or sorry, the reciprocal plane which was studied by Nick Proudfoot and David Spire in the early 2000s. Okay, so this is another example of a collapsing. All right, so in general, when you've got some vector bundle and you collapse it, and you're under the you're in the case when the collapsing map is a birational isomorphism, a bunch of information, interesting information about this vector bundle is reflected inside of the collapse variety. So I'm going to give you two results that tell you what kind of information is remembered. Okay, so the first result I'm going to call proposition C, because it is like a statement about Chow theory. So like intersection, the intersection. Okay, so I've got E and CM. F is going to be CM. So the associated quotient bundle, which is CM modulo E. And so let's assume I E is rational isomorphism, that the degree of Y, so the degree of the collapsed thing can be computed as a degree over the base of this bundle. So it's going to be degree over X of a particular Chern class of associated quotient bundle. So what do I mean by degree on the left side? I mean, like, so the first thing to notice is that the collapsed bundle is like always a cone, meaning that like it's cut out by homogeneous equations. And the reason for that is that the vector bundle E has like action by scaling. So it has like a one-dimensional torus acting on it. And so the degree here is going to be like the degree of the associated projective variety, which here you can think of as take a hyperplane in CM whose dimension is complementary to the dimension of the collapsed thing, intersect them, and then look at the number of points that are in that intersection. That's what this degree is. This is like a degree in the sense of like the Chow-ring of X. So there's another. This I kind of think of this as a like commutative algebra information. Okay, so there's and this I think of as like some well, seems like more so information about the vector bundle. So there's another result, which I'll call proposition K. And so it says if Y additionally has, well, I guess is normal with rational singularities, then you can write down a formula for the K polynomial of what this variety is. Let's see. is given by the following formula. So it's sum over I. You're going to take an Euler characteristic of an exterior power of dual of F. And it's a generating for those things. Okay, so what's happening here? So the K polynomial, this is you should think of this as like this this affine variety. It has its coordinate ring, and you can write down the Hilbert series of that coordinate ring. The Hilbert series ends up being a rational function. The K polynomial is the numerator of that rational function. And it turns out that the numerator of the Hilbert series of this variety can be expressed in terms of Euler characteristics of exterior powers of the dual quotient bundle. Okay, so in general, I would think of like these numbers as like mysterious, and this K polynomial is like something that's like very computable.
Couldn't something like proposition C be true without the birationality assumption?
You need to put like a factor about like,
I somewhere.
yeah, that's right. Okay, so example 2, continued. So I can use proposition C, proposition K to compute the degree and the K polynomial of the reciprocal line. Okay, so in this case, what I would get is that the degree of the reciprocal plane here is going to be the degree over the wonderful variety of the top Chern class, or the dim X dimensional Chern class of the associated quotient bundle. It turns out that in that case, it's just beta to the R minus 1. And this was computed in paper of June and Eric Katz. The constant term of the reduced characteristic polynomial of the matroid. In particular, and then there's another formula here, which says that this is going to be the number of NBC bases of matroid of L, which if you don't know what NBC bases is, then you should just think it's think of this. Okay, so that's what happens in the when computing the degree. So this actually recovers a result of Proudfoot's fire. And then we can also give a formula for what the K polynomial is. So the K polynomial is going to be, okay, so what you need to do is you need to compute this sum of Euler characteristics. And so how do you do that? It turns out that there's a theorem that allows you to express this K polynomial in terms of the top polynomial of the matrix. 1 minus Q to the N minus R, where R is the rank of the associated matroid, Q to the R, and then you get the polynomial matroid of L evaluated at 1 over Q, 0. Okay, so what this does is you apply proposition K, and then you apply the exceptional Riemann rock isomorphism plus the big tut formula in my paper with Chris Burr, Hunter Spink, and Dennis Sang. And this is what pops out. Okay. So the moral here is that if you know how to compute the things on the right-hand side, then you can get all kinds of interesting information about the collapsed variety. And but in many situations, we don't know what goes on the right side of either of these formulas. And in that case, what you can do is you can compute the left-hand side, you can compute the degree, or you can compute the K polynomial using some other methods. And then you can learn things about generalizes and Euler characteristics of exterior powers. So that's, so now I'll get to my main example.
Yeah.
Okay, so this is going to be the Schubert variety of a pair of linear spaces. And so I'm going to have Xn is the Bermuda-Hedro variety, the toric variety associated with the hedron. And I'm going to have L1 and L2. These are going to be fixed linear spaces of Cn. And so S of Li, this is going to be the is equal to the vector bundle on Xn that is equal to the pullback of the following. So there's a map from this, the toric variety of the Bermuda-Hedron to the porous orbit closure, big T orbit closure, through this particular linear subspace in whatever Grassmannian it lives in. So this is contained inside of some Grassmannian GR1 n. And so I'm going to pull back the tautological bundle along this, the tautological subbundle of the Grassmannian along this, this map. So this gives me some vector bundle over the Bermuda-Hedron that is associated to each of these linear subspaces. Okay, and then the Schubert variety of L1, L2 is the collapsing of S of L1 plus S of L2. And I'm just going to denote this as Y of L1, L2. Okay, so I can just say explicitly what this thing is. So Y of L1, L2, I can describe it as a closure of some relatively easy to understand set. So what you're going to do is you're going to select an element from one of your subspaces. You're going to permute it by a torus element. You're going to select an element from one of the other subspace. You're going to permute it by the same torus element. And that's it. Okay, so U is an L1, W is an L2, and T in torus. And yeah, so it's the true of this thing. Okay, so this is some subvariety of C and plus Cn. Why is this a Schubert variety of a pair of linear spaces? How does this contrast to the Schubert variety of a single linear space? So remark is that if you take L2, would just be the span of the all ones vector, then y of L1, L2 is the affine cone over the usual Schubert variety of L1. Okay, which is some subvariety of a product of P1s. So in particular, you can ask the following question. Okay, so if you were to quotient this variety by the natural torus action that it has by the n torus, then this gives you a subvariety of P1 to the n. And because I know that people have been thinking about this kind of thing lately, this has a C star action. So P1 has a C star action, and you can ask what happens when you take the further quotient, Y1, 2, L1, 2. And then we quotient again for the C star action. And I have a guess for what this is. I think that it's like somehow it should be like the difference of the two Bergman fans of the so it should be like the Bergman fan of L1 minus the Bergman fan of L2. But it should come about by tropicalizing the quotient of the two the quotient of the two spaces, linear spaces. Okay.
This variety?
Yes. So the question is, what is this variety?
It's not a fan in particular.
No. Well, so yes. So you get the wonderful compactification if L2 is equal to the span of the all ones vector. So and like morally, what's happening is like you're taking the difference of two Bergman fans. So I feel like there's some kind of interesting geometry happening here.
This is a subvariety of the permutation.
Yes. Okay, so
I'm not sure what you mean by difference of the ones.
like I mean the not the Minkowski sum, but like the Minkowski difference. Okay, so in the
Did you just say again, what quotient did you do?
which quote
What quotient?
this like iterated quotient. So
No,
this
no, what type of quotient?
this is Chow quotient.
Can we say a word about Chow quotient?
No, not right now. Okay, so sorry. So the things that I would normally be interested in this variety are the things that are reflected in proposition C and proposition K, which is I want to know things about the degree of this variety, and I want to know what about it, what's the K polynomial of this variety. And so since I don't have good formulas for what the items occurring on the right-hand side of those formulas are, I don't know what the Euler characteristics of the exterior powers of the associated quotient bundles are. I don't know what the products of the Chern classes, or I don't know what the Chern classes of these associated quotient bundles are going to be. I need a different way to study these. Okay, so this is part 2. of the talk, which is on Vogner definitions.
Y one is Y the one else. It's a cone. Is it a cone over something? Is the projectization like smooth? Like what is the projectization of Y one? Like is it? Do you know anything about it?
Yeah, I know, I mean, so I don't have enough time to tell you what the affine or what the coordinate ring is, like the homogeneous coordinate ring of this quotient is. But I do have enough time to tell you what the initial ideal is.
Is it like a smooth variety or is it not smooth?
No, it's it's coming up in the next theorem. Hopefully you'll be satisfied. Okay, so I'm gonna Grosvenor deform Y of L1 L2. And so for this, I need to let D of, so M1 and so MI is going to be the matroid of LI. So D of M1, M2 is going to be the matroid that I introduced in the last talk, which is the diagonal Dilworth truncation of M1 and M2. So it is the matroid whose base polytope is E of M1 plus E of M2. So the base polytope of M1, Minkowski sum the base polytope of M2, and then minus a simplex here. And so this requires probably more time than I'd be willing to, or that I can give it right now. But by this, I mean this polytope right here is its points are such that if you add in any point from the normal simplex, you land inside of the Minkowski sum. Okay, so it's entirely plausible that this polytope would be empty. If it was empty, then you should probably replace these things by their independence polytopes. And it turns out that this polytope being non-empty is actually equivalent to this thing being birational to the associated bundle. Okay, so I'll often just this this matroid is D. Okay, so this is page. Okay, so here's a theorem. What I'd like to be able to tell you is what are all the equations that vanish on this variety. But and I can say quite simply that they are some determinants that are parameterized by the circuits of this matroid. I'm going to, so let I of L1, L2.
Sorry, you said this variety, you mean this?
No, this one right here, this affine variety. So its equations are parameterized. So like a minimal generating set of equations is parameterized by circuits of this picture. Okay, so this is the ideal Y of L1, L2, which is going to be some ideal inside of a polynomial ring in two sets of variables. And I'll denote this ring by A. Okay, so the first part of the theorem says what the leading term ideal is. I of L1, L2. And I'm going to use a monomial weight order, W. And so this is going to be the ideal generated by X sub I2, Y sub I1. So these are square-free monomials, and so you're gonna multiply the monomials that are given, or you multiply the monomials corresponding to the elements in a particular subset. And you're going to get where I1 disjoint in I2 is a circuit D, and the expression and x of I2, y of y1, oh, I should say I sub j is independent in M sub j. So this should be independent in M1, this should be independent in M2. And so I want this to have largest W weight all such decompositions of the corresponding circuit. I1. Okay, so I can look at the circuit and I can look at all the ways to break it up as some independent set from I1 and an independent set, or sorry, an independent set from M1 and an independent set from M2. And then I want to find the one that achieves the maximum weight for my given one weight order. Okay, so that's the first part of the theorem. It tells us what the initial ideal is. The second part says that the coordinate ring A mod the ideal of y of L1, L2 is normal Cohen-Macaulay, and it has rational singularities. Okay, and the last part is that if D has rank of M1 plus rank of M2 minus 1, then the map from the bundle to its collapse is birational. So this kind of, hopefully this answers your question. We know essentially all the things that you would want to know about this variety. We know how it's normal, it's Cohen-Macaulay with rational singularities. We know desingularization of it, and we know a Grosvenor basis. In fact, a universal Grosvenor basis for its defining ideal. Because of these results, I can apply proposition K. Oh, so I should say something else. So because I get a square-free monomial ideal here. Well, this parenthesis extends all the way to the end over there. Because this is a square-free monomial ideal, I can associate a simplicial complex to this square-free monomial ideal. Okay, so delta sub W of M1, M2 is going to be the Stanley-Reisner complex associated to the leading term ideal of I of L1, L2. And the point here is that this, the initial ideal only depends on the two input matroids. It doesn't depend on the actual linear spaces that they came from. Okay, so if I apply proposition K, what I get is the following. So I'm going to apply a slightly refined version of this. It's going to say that the K polynomial of this complex is going to be, so it's the sum over all J of the Euler characteristic over the permutation variety of some exterior powers of some quotient classes associated to the two bundles. So here, I suppose, in order to be like super technically correct, I should have said L1, L2.
Dual.
Dual, thank you. Except that in this paper with Christopher, Hunter Spink, and Dennis Singh, we proved that the classes of these bundles in K theory only depend on the associated matroids, and so this expression you can extend to any pair of matroids. Okay, so this is good because you can now use Stanley-Reisner theory to compute the K polynomial of this simplicial complex. The simplicial complex, in the case that M1 and M2 are realizable over a field of characteristic 0, will inherit some of the properties that we had over there. In particular, it will inherit the Cohen-Macaulay property.
K polynomial of the simplicial complex, you just made numerator of the Hilbert series?
Yes.
You know this identity is true for any matroids, not just those coming from L.
So that's yes, that is. So I can tell you that the identity is true. So in fact, this formula is true whenever this diagonal Dillard truncation has rank given by the rank of M1 plus the rank of M2 minus 1. Okay. This is saying that the like somehow this was that y of L1, L2 was birational to the bundle. Right. We can say some things about what happens when the rank is not what you expect it to be, but it's more subtle. And I can't get like the best version of this. I can't draw this assumption right now. Okay, so I've got just a few minutes left. Oh, I've got 10 minutes left. So now what I want to do is I want to talk about how to extend this result to all matroids, not just matroids that are realizable over a field of characteristic 0. Okay, so I'll do part of this by pointing. This expression right here this is bivaluative on matroid-based polytope.
Sorry, could you write the variables?
Sorry, what was that?
This last thing is a polynomial in what?
Oh, I forgot to write the variables. So it should have been times negative u1 to the I times negative u2. Thank you.
And we have two because it leaves the product. Yeah?
That's correct, yes. Okay, so each summand here, each Euler characteristic is bivaluative in the, so it's valuative in this factor and it's valuative in this factor, and I'm taking it as a product of these things, so it inherits the natural sense of being bivaluative here. And so the idea to extend this this formula to any simplicial complex is to prove that the K polynomial of this simplicial complex is is to show that this thing is bivaluative. Then I will know that they are bivaluative. I have two bivaluative invariants that agree for all matroids that are realizable over all pairs of matroids that are realizable over a field of characteristic 0. There is like a minor caveat with this thing right here, but it turns out it's not a big deal in the end. And if you have two bivaluative invariants that agree over all realizable things over field of characteristic 0, it turns out that they agree for all input matroids. So it's sufficient to show that this K polynomial is bivaluative. Okay. Section to all. Okay, so what we need is we need to come up with a way to express the K polynomial of this simplicial complex, whatever it is, whose Stanley Reisner ideal is this thing. We need to come up with a new expression for this K polynomial that that is like manifestly bivariate or bivaluative. And okay, so how do I want to do this? And stuff. Okay, so here's the idea. Is that if I intersect the Chern classes of M1 and M2, so I want to do I and J, where I plus J is equal to N minus 1. This should be telling me information about the multi-degree of the associated variety. Okay, so this is telling me information about the multi-degree. So the Z2 multi-degree of Y of L1, L2. So this sort of is suggesting that like the multi-degree should really be a bivaluative invariant as well. And and these Chern classes are also known to be bivaluative. So what I'll do is I'm going to compute the product of two Chern classes of M1 and M2. But now I'm going to have no restriction. So on the I and J. And so how am I going to do this? I want to do this using what's called the fan displacement rule. So I can think of these Chern classes themselves as fans. So these can be of fan intersections. And to do the stable intersection, well, to intersect two fans and to have them compute intersections in the Chow ring of the permutahedron, what you do is you take one of the fans and you wiggle it a little, you take the other fan, you wiggle it a little, and then you literally intersect the two translated fans. So there's like a whole procedure to do this, which I've clearly run out of time to tell you, but I did prepare a little bit more. What I wanted to show you, so I drew a picture of what happens. Okay, so what happens is that when you intersect any two of the churn classes of M1 and M2, you sort of get like a partitioning of space. So this space right here is R3 multiplied R, the diagonal copy of R inside of there. And so you can assign to every point inside of Rn mod R, you can sort of see how that point sits relative to these two fans. And so I've drawn what each of the churn classes looks like here. What's the fan associated to each of them? And then I've drawn the partitioning of R3 mod R into cells. And what you can do is you can associate a monomial to each one of these cells. And then you can associate the lower dimensional cells here. You're going to do like the GCD of the cells that are on its boundary. So for example, this one right here would get X1, X2, Y1, Y2. Right? And so these, the zero dimensional intersections, correspond to doing like the actual top degree intersections of my so my zero dimensional intersection of churn classes. And so these correspond to the facets of my, like of the Stanley-Reisner complex of, so the delta M1, M2. And all the rest of these things correspond to lower dimensional faces inside of the external activity complex. And so the thing that I'll just say this part, which is that all the facets of delta of M appear as a monomial associated to one of these cells. And but not every face of the external activity complex appears as a something over here. But it turns out that enough information appears over here to extract the K polynomial of delta of M1 and M2. And because these churn classes are manifestly bivaluative, or this product of churn classes is bivaluative, the expression that we get for the K polynomial will turn out to be bivaluative, and that'll extend this this formula to all things matrix. Okay, so I'm done. Thank you.
Questions for Andy?
That's just a bit more of the background motivation. Why did you want to contribute?
So
Remind us how this is related to Spire's conjecture.
So Spire's conjecture concerns the Euler characteristic of wedge of S L.
That's your interpretation.
No, this is like so the way that this is like a 2010 paper of Spire and Alex where they related these Euler characteristics to his like initial definition of the his G invariant. This dual, yeah. One dual, yeah. So I knew that these things were going to be interesting. I knew that, but I also knew that like these methods, they require you to use like a sub bundle of a trivial bundle, and that kind of forced my hand and meant that I had to use like either like an S, like I had to use two S's in order to do that, and so I just started like taking the only obvious things that I could do. But there is some things that get that are kind of lucky here, which is,
I didn't understand the alphabet.
So in the end, his M1 will be equal to M2.
Yeah, okay, so are you interested, do you have applications for M1 not equal to M2? Or do you need to think about M1 not equal to M2 in order to prove things about?
so I think that this idea of, so Spire's invariant, it's valuative. It's actually like co-valuative or something, but let's just pretend that it was a valuative invariant. But it's kind of a strange thing because it's like, if you look at this expression right here is not valuative. This is something that showed up in June and Federico and Graham's paper, and where they have some expression that you wish were valuative, and it is valuative, but you can't see it from this expression. This thing is not manifestly valuative, right? It's quadratic roughly. And so separating out the case from where L1 and L2 are different is like actually helps you considerably in understanding what's going on. And so you wouldn't be able to do any of these things if you were, or you wouldn't have been able to see any of these results if you had only restricted to L1 equal to L2 the whole time.
What do you get, 3 matroids?
Yeah, so then instead of having D, which is, so then what you would get is polytope of one plus a polytope of the other one plus the polytope of the third one minus a simplex. So the true miracle, or one of the true miracles that happens here is that when you just have 2 matroids involved with that, that you actually get a matroid coming out of that. You'll get a polymatroid in general.
But like the Stanley enrichment theory is going to be much more complicated with 3, right?
Yeah, so I think that yes, it'll be much more complicated. I think that there is like a sort of more simple case, which is you should do M1, M2, U1 add. Because in that case, when you add up the 3 base polytopes, you'll end up canceling the simplex. And so the polytope associated to this will just be the Minkowski sum of these 2 base polytopes. Yeah, Kyle.
How special is the normality here? Do you expect any time you do a construction of this type that you'll get something normal?
So what, I don't know how to, so you can do this construction where you did S of L1 plus S of L2 plus like just any number of sums of S's.
Yeah.
Right? I don't know what happens in part A. Part B just will hold. That's no big deal. Part C, there's the more bundles that you add in, the easier it's going to be to show that you're birational. Yeah.
Like what goes into the proof of normality? Can you just see it directly?
I definitely cited this. The family of ideals that occurs here is a special example of something called like a Cartwright-Sturmfeld star ideal. And it turns out that and actually and this also is Cartwright-Sturmfeld. And I believe that when you have a CS ideal coming from a pair of linear spaces or any linear space, you always get normality.
What's the homology class of this torus quotient is like P1 to the n?
So the homology class is the basis enumerator for D. In general, I had to cut like a ton of stuff. But if you were to do L1, L2 up to let's just say L3, you would get the lattice point enumerator for P of M1 plus P of M2 plus P of M3 minus a simplex.
Do you know anything else about this resolution singularities, like the fibers, things like that?
I don't know what kinds of things you want to know, like is the fiber.
Well, like,
so in general, if you just select a point like it's right here. So if I select one of these points and I say like, what's the fiber? It should just be like a torus. But then like, as you pass into the closure, I don't know what the fibers are going to look like.
So maybe part B is a consequence of the fact that this homology class is like 0, 1.
Correct, yes. Yeah, 0, 1 homology class is huge in all the arguments. But it's funny because it's like you look at the homology class here, and what you do is you learn information about the homology class in P n minus 1 plus P n minus 1. So we sort of, and both of these things like have y of L1, L2 sitting over it. So I've played the two ideas off of one another.
Is that quotient smooth or?
I have no idea. I mean, yeah, I don't know.
So when L2 is U1N, that
Then,
It's,
projective reciprocal plane?
no, it's wonderful.
Oh, it's
variety.
wonderful.
Wonderful.
yeah, so it actually depends on which, if you were to use the other C star that's acting here, right? Instead of like doing on the first part of every homogeneous coordinate, you do it on the second part, then you should actually just get like L. But here it sort of highlights, well, so, okay, so one of them is like L1 over L2, the other one.
Any other questions? If not, let's just